There he is. Right. What's this? Oh no, I don't believe it. This is a ticket. It's a ticket to Yui. Who the hell wants to go there? Oh no. Well, at least, you know, he's lost his ticket, so he's gonna have to come back now. Haha, right, great! Sam's coming back, yay! I just need to wait now. Hang on. My video! New series! Oh, hello everyone, you join me once again for another revision series. We've done molecular methodology, we've done evolution, we've done acquisition of behaviour, we've even done a little bit of insect biology. Now, in this series we're going to be doing something completely different. We're going to be doing parasite biology, and this is actually going to be the last revision series I do this year, simply because I wouldn't have time to do anything else on my degree programme. As much as it is helping me to revise, it's not physically possible. So let's get stuck in them. Parasites, they're fascinating things. Now, if we take the broad definition of parasite, well, that includes the bacteria and the viruses. We're not going to focus on them too many. We're going to focus primarily on this series on two types of parasite. The protozoans, which are the protists, so the unicellular eukaryotes, contain some of the deadliest parasites on Earth. And also the helminths, basically the worms, right? I could just say worms, because to be honest with you, the word helminth isn't actually taxonomically very useful, because it's actually a polyphyletic group. Because when we say helminth, we're talking about the platyhelminths, the flatworms, and the nematodes, which are the roundworms, okay? So it's hardly that useful. Now, this episode's all about parasite transmission, okay? So this always involves moving from one host to the other, right? And there are two different potential life cycles you can have as a parasite, right? You can have a direct life cycle. This is a life cycle which only involves one host. It's called direct because you're directly moving between hosts, the same host. Now, that doesn't mean that there can't be any free living stages. In fact, there usually is. Okay, especially in many of the helminths, there's actually a stage which is external to the host, and then there's fecal-oral transmission. Okay? On the other hand, there's indirect life cycles. Now, this is different because it involves two or more hosts. So it involves a definitive host and an intermediate host. Now, how do you know which one's which? The definitive host is where sexual reproduction takes place, okay? And the intermediate host is where it doesn't, right? There's still development in the intermediate host, but just not sexual reproduction. So therefore, just a little, side point, it's quite interesting that actually the definitive host of the malaria parasite is the mosquito. Because if you look into the life cycle, that is where the sexual reproduction takes place. You have the microgametocyte and the macrogametocyte coming together in the mosquito. But that's a completely different story then. So we'll talk a little bit about free living stages first. So a property of direct life cycles. Okay, although you can get them in some indirect life cycles as well, moving between the definitive and the intermediate hosts. Okay, now these free living stages are usually environmentally resistant, and they usually occur in large numbers because this increases the chance of, some of them being taken up by their hosts, by the definitive hosts. So because they're environmentally resistant, they persist in the environment and are often attracted to their hosts. Now we're going to look at an example, and this is Ascaris lumbricoides, which is a nematode parasite. Quite a nasty thing. In fact, they're can get quite big. The female can get up to 35 centimetres in you, and these live in the gut, but they have kind of a weird life cycle, because when you ingest them for the first time, they're not actually at the correct infective stage. Now before I go into that, let's go into the life cycle of nematodes. It's very, very simple. Basically you start off with an egg, then there are 4 larval stages, so they're called L1, L2, L3, L4, and then you get a final molt, because remember nematodes have an external cuticle that will molt into an adult, and then that'll lay eggs and the cycle will continue. Okay, now usually the infective stage in parasitic nematodes is the L3 stage. Okay, and we're going to explain why that may be in a second. But here you ingest the L2. Now, so the nematode has to do something else. So it goes into your gut, then it bursts through your gut, right, into your circulatory system and goes up to your lungs through the portal vein. Now here, it'll break through your alveoli and then you'll cough the nematode back up. Then hopefully, well, the nematode wants you to swallow it again, and by the time it gets back into your gut the second time, then it's in the L3 stage and ready to be infective. And then from there it can cause a whole load more problems. In fact, it can cause obstruction in various, organs. Another thing, if a female is on its own, this is kind of cute, right? If the male's there, it would usually wrap around the female and sort of squeeze the female. Now the female likes that. It's kind of cute, nice little cuddle, right? So when a female's lonely, it will try and get itself into tight spaces, like in the bile duct, where, it's quite tight. So it gets that sort of squeezing sensation which she likes. Oh, it's heartbreaking, isn't it? But anyway, we've gone off track. So, Ascaris lumbricoides. So, eggs don't contain developed embryos, okay? So when the eggs are laid, this is a fecal-oral transmission cycle. So you poo out the Ascaris eggs. So if you poo them out, if you directly ingested, let's say, this is a horrible thought, if you ate your own poo, after, with Ascaris eggs in it, then those Ascaris eggs won't survive. They require time external to the host for them to develop into that L2 stage, which you then ingest, then cough up and back on. Okay, like what I just said. So they require time external to the host. Now the point in which they develop into a stage which is infective is thought to be temperature development. And this is shown in a species of Ascaris which infects pigs, not humans, because it's a bit unethical to do experiments on humans with this sort of worm. So it's shown that Ascaris infections are greatest in the spring and summer, which is synchronous to the time where piglets are born. Now, if you get a load of young pigs, that means very young immune systems, so not particularly highly developed, so that would increase the chance of success for the parasite in propagating and reproducing and producing more Ascaris and blah blah blah. Okay, so it's very clever, these nematodes. Also, these fruit-living stages are resistant to freezing, desiccation and even disinfectant, so they're pretty tough little creatures. Okay, now let's go on to another example. It's another nematode, well, 2 species actually. There's Ankylostoma and Nicator, and these are 2 different genuses of hookworm. And instead of you ingesting it, they bore through your skin. Okay, so in areas where hygiene isn't particularly great, right, and there's an outside toilet or something and you have to walk to the toilet, and if you're walking barefoot, then those L3 larvae actually bore through your foot and into your body. Okay? Like Ascaris, this is another coughed and swallowed life cycle. So it is the L2 that bores into your foot, then it goes to the bloodstream, through the lungs, then coughed and swallowed again. Okay? And then it goes into the intestine. Now, one of their strategies is when the L2 molts into the L3, it retains its L2 cuticle, okay, on itself. It's a bit like, remember what we were talking about in the last video in insects, about the pluparium of some diptera flies? Remember that? Oh, good time. Anyway, so L2, so it's got an extra layer of protection there, okay, very useful. Now, like Ascaris, these nematodes have an extremely high fecundity, okay, and they are attracted to warmth, okay, so they finally become active in the host serum. So this suggests that there are specific host cues that these parasites use. Oh, God, that was a nice riddle, wasn't it? Anyway, God, I didn't realise I was going to say that. Okay, so and also another thing to mention, that these sort of parasites, transmission occurs in the damp. If there's a dry period, then these parasites remain dormant within the host. Now this brings us on to the very interesting topic of the evolution of parasitism, specifically in nematodes here. Okay, now depending on who you ask, okay, it is thought that nematodes could be the most abundant group of animals on Earth. Now you may think, God, he's contradicting himself, because my last video was basically saying how arthropods are by far the most abundant animal group on Earth. But a lot of people think, because nematodes are so small, inconspicuous, of course they're not all parasitic, there's loads and loads of simply free-living nematodes, a lot of people think that they're likely to be a lot more specious, okay, but it's a matter of debate. As it stands, of course, the clear champions are the arthropods. But anyway, we won't go too much into that. But it's thought that this parasitism might have evolved at least 5 times independently. Maybe even up to 7 times, okay? So this is a case, of course, of convergent evolution, okay? And it's thought to have been developed through increasingly intimate associations with your host. Environmentally resistant larvae could have made it possible they could stay for longer periods within their host. So they could stay dormant within their host. And this is in the form of dour larvae. One interesting word. So it is likely that nematodes began to live with their hosts for longer periods, perhaps in body cavities and places like that. Additionally, there are also many scavenging species of nematodes, so non-parasitic, but nematodes which feed on dead animals, right? So it could be that this increasingly intimate association with your food source might have evolved into parasitism, okay? Considering that, this has evolved 5 or 7 times, it could have been a mixture of these, okay? But let's focus more on what I said before, on the dour larvae idea. So dour larvae are these environmentally resistant dormant stages in nematode worms, okay? And they're seen in non-parasitic nematodes, and this is what gives us this idea. Now, the L3 infective stage, which we've said is usually the infective stage of nematodes, okay, closely resembles the appearance of these dour larvae, in the sense that they're both non-feeding, they're both long-lived, and they're both developmentally arrested, right? The L3 larvae of parasitic nematodes can't carry on to develop unless it encounters its host. On the other hand, we also have these entomopathogenic nematodes, okay? And a great example here is Steiner nema. Now these nematodes carry symbiotic bacteria within them, right? And when they encounter a host, the bacteria kill it, okay? The bacteria kill the host. So then you've got a dead body, which then the nematodes feed on, okay? So these aren't true parasites in their true sense. It's the bacteria that are killing the host. The nematodes are just there for the rewards after, okay? It's quite a nice relationship, really. But it does give us an idea on how parasitism may have come about. Okay, we're now going to focus on host-host transmission and the adaptations that facilitate host acquisition. Right, and our first example, we're going to divert away from nematodes now. We're going to look at the platyhelminths, the flatworms. And one of the most important, I'd say, parasitic flatworms are the schistosomes. So we're going to look at an example of Schistosoma japonicum. Okay, now the digenians are a group of exclusively parasitic worms, okay, and they're particularly interesting because, as the name suggests, they have indirect life cycles, so they have a definitive and an intermediate host, But the intermediate host is almost always a snail. Okay, quite interesting. The Schistosoma japonicum is a particularly important species, and here we see the timing of, we're not going to go into the whole life cycle of schistosomes here, but basically snails release cercariae, and these are the infective stages which infect the definitive hosts. Okay? Now, the timing of cercarial shedding of the snails, okay, so the timing of when these cercariae are released from the snail is in tune with the timing of their definitive hosts, of when, you know, these hosts are likely to be in contact with the cercariae. So their circadian rhythm, if you like, is in tune with that of their hosts. And this was shown here because the timing of cercarial shedding differs depending on the habitat. So this species can be found in hill or marshland regions in China. Funnily, not Japan. Presumably you can find them in Japan as well. It's Schistosoma japonicum. Now, if you live in a hill area, then your definitive host is going to be a rodent of some sort. Okay? Now, they come out at night, so the timing of the cercarial shedding by the snails should be around night time. Okay? However, remember, we're talking about the same species here. If this species occurs in marshland, where the definitive host is likely to be a diurnal cattle species which graze around the land, then it makes sense for you to release your cercariae during the daytime. Okay? So it's extremely clever. Right? Going back to our friends the nematodes, we're going to be speaking about the filarial nematodes. These are the nematodes which, when they give birth, they don't release eggs, they release miniature infective forms called microfilariae. Okay? And these are taken up by an insect vector. Okay? Now, classic examples include Onchocerca volvulus, which leads to river blindness or onchocerciasis. We also have Wuchereria and Brugia, which leads to the rather dramatic symptoms of elephantiasis. Okay, and if you look up the pictures on Google, I'm not going to show you because I don't want to shock you with graphic images, you'll see why it's called elephantiasis. So, as I say, all species produce microfilariae, often abbreviated to MF, because, you know, biologists are lazy. And these circulate either in the tissue or in the blood. Okay, and they're taken up by an insect vector. So let's say in the case of Onchocerca volvulus, it'll be a black fly. Okay, from there it will develop from L1 into L2, then L2 into L3, and the L3 stage is now going to be the infective form, which infects a vertebrate host, so a human. Now, the presence of microfilariae in the peripheral circulatory system was studied by F. Hawking, who is none other than the father of the great Stephen Hawking. So, little did you know that Stephen Hawking's dad was a parasitologist. You know who made the better life choice, right? I'm not going to answer that question. But anyway, so he found out that the microfilariae peaked in the peripheral blood system at around midnight, more specifically between 10 p.m. and 2 a.m. at night. Okay? And this coincides with the biting behaviour of the insect vector. So, just like the Schistosoma japonicum example, these worms are fine-tuning, you know, when it's best to go out into the peripheral blood system, depending on the circadian behaviours of the vector. And it's thought that this change in behaviour could be triggered by oxygen level. Now, in these indirect life cycles, you might, overlook the fact that these nematodes are going from one organism into a completely different species, okay, in which the environment is likely to be very different. For example, in the insect, oxygen levels are actually pretty low compared to in the mammal, and also the more of an ambient temperature, because remember, these aren't endotherms like we are. Okay, so it's going to have to completely change the way it lives. So it's going to change things like gene expression, morphology, physiology, biochemistry, you know, all these sort of stuff. So it's a big, big step, right? And probably one thing that's in the nematode's favour here is this idea that they molt. Because molting is great because it allows you to change morphology. So this could be a way that these parasitic nematodes may have evolved and specialised. Okay, we spent this whole video talking about helminths. I saw we were talking about protozoans as well. So here's our first protozoan example. This is Toxoplasma gondii. God, I sound like a big magician or something. That could be my magic words. Toxoplasma gondii! God, there you go, you disappeared. Anyway, right, so Toxoplasma gondii is a parasite which changes host behaviour. Now, how does it do that? Now, this is quite an interesting one. It infects, the definitive host is the domestic cat, right? Okay, what's special about that? But what's interesting is that the intermediate host can be any mammal or bird. Okay, absolutely anything. Now, they usually stay dormant within their host. In fact, there's an incredible statistic that says that 25 to 50% of the world's population, humans, right, are infected with Toxoplasma gondii. What a crazy thought, but you don't need to worry because they're usually in the dormant form, in the form of bradyzoites. Okay? The only time where you may think about worrying is if you're infected whilst you're pregnant or if you have AIDS. Okay? But anyway, that's not related to the subject. Now, in the wild, the intermediate host are rodents because these are things that cats prey on. Okay? So that's how the life cycle could be completed. Because obviously if we're infected, a cat is never going to eat us, is it? So we'd be a dead end for that parasite if we got infected. Okay? So we're thinking about, in the wild, rodents. Okay? Now, what is really interesting, this is a fantastic experiment, I think. It was found that in infected rodents, there was less avoidance, because obviously rodents are going to want to escape cats at any given opportunity, right? It's like Tom and Jerry. Now, we've all seen Tom and Jerry. But if Jerry was infected with Toxoplasma gondii, he is more likely to visit Tom's urine. Okay? So there's a decrease in avoidance, right? So this increases the chance, because of course cats always hanging around their own urine, aren't they? That these cats will prey upon the rodents and the life cycle will be transmitted. So these parasites, these small, unicellular parasites are having a direct effect on the host's behaviour. And there's an argument that, anything we do, any of our behaviour could be controlled by parasites. Because obviously we're likely to be infected with quite a few parasites, probably not doing us much harm at all, but still influencing our behaviour to some extent. Okay, obviously not completely, but it's quite an interesting thought, isn't it? But anyway, next example is not actually a human parasite, it's Hemontius contortus, and this is one of the main ruminant parasites who infects things like sheep. So here, genetically resistant sheep were selected and they observed their behaviour, right? And it was shown that these genetically resistant sheep fed less on tussocks, okay? Places where they could potentially take up these parasites. Now, our last example is going to be Dicrocelium dendriticum, which is probably my favourite of the episode. This is another digenian, so it's like Schistosoma. But here, the intermediate host is not just a snail, but also an ant. Okay, so there's two intermediate hosts in this life cycle. So, Cercariae are taken up by the ant, and these Cercariae migrate into the sub-esophageal ganglia. Okay, so this is part of the nervous system of the ant. And here, the Cercariae sort of take over the ant's mind, if you like. So ants would normally, at night time, they'd go off into their nests for the night, stay out of harm's way. Well, when they're infected with Dicrocelium dendriticum, they climb up onto the tip of a blade of grass and just hang there. If they're right at the top of a grass blade, then they're more likely to be grazed by a sheep or some other ruminant. Through this completing their life cycle. So quite a few examples there of how parasites can influence host behaviour to facilitate their transmission. Brilliant. That's all we've got time for today. Next time we'll be talking about host and parasite populations, okay? But for the moment, see you next time.